So we had an entire video on GitHub Actions without showing any GitHub Actions. Will I go 2 for 2? Let's find out. Welcome to this video on Azure Machine Learning. My name is Kevin Fiesel, and I am the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, we set the stage for working with GitHub Actions. We created a service principal in Azure Entra ID, granted it the appropriate rights, and created relevant secrets in our GitHub repository. Now in this video, we are going to create GitHub Action workflows for performing training and scoring operations when we update relevant files in our repository. For this introductory section, I'm going to hit on two major topics: a primer on GitHub Actions, as well as some discussion on branching strategy. Branching strategy isn't absolutely required here, but I know a lot of data engineers and data scientists have trouble with this, and so I want to share some high-level thoughts as they will play in how I've defined the GitHub Actions workflows we'll review. First up, GitHub Actions. GitHub Actions are defined in YAML format and look a bit like this example. Each YAML file defines a workflow. The workflow has a name as well as indicators on when we would trigger this workflow, such as a push into this repository. A workflow also has one or more jobs. These jobs can run either in parallel or sequentially if you use the needs attribute in a job and specify the name of some other job that you want to run before this job. Within each job, we can have one or more steps. Each step is some action that we take, such as running a command line script, checking out a repository, connecting to Azure, saving a file to Azure Blob Storage, this sort of thing. Sometimes you'll need to run your own custom shell scripts as part of GitHub Action workflows, but there are also a variety of actions already available to you in the GitHub Marketplace and in open source repos. This image shows you how to reference one of these using actions/checkout at v2. This points to a GitHub repository in the Actions organization called Checkout, and we are specifying version 2 of the action in this image. By linking these steps together, we achieve some sort of desired outcome. Hopefully. Maybe. Possibly. Speaking of triggers for this workflow, there are dozens and dozens of events which can trigger GitHub Actions workflows to run, but here are a few of the most common ones I've seen. The workflow dispatch event is for when we want to run a workflow manually. We can schedule a workflow if we would like it to run at some time during the day or some time interval. Schedules accept cron syntax, so I would recommend a good website for double checking your cron syntax to make sure you get it right. I'll link one of those in the description below. When we push into a specific branch, or into any branch if we want it that way, we can execute a workflow. And the fourth one I've seen pretty frequently is executing a flow on pull request. This might do something like, say, build the code, including the changes from that pull request, and then run a set of unit tests and integration tests against that code to make sure that a code change doesn't break anything. But these aren't the only events that we can use, so I've included a link to the events and you can get an idea of just how flexible this GitHub Actions system is. So that's all I've got in my brief intro to GitHub Actions. Now I'll meander a bit on the topic of branching strategy. This applies to all distributed version control systems, such as Git and... okay, let's face it. As much as I liked Mercurial and I thought it was better than Git for most use cases, the likelihood that you're going to run into Mercurial in the wild is almost zero. And absolutely zero when we're talking about GitHub or Azure DevOps, as neither one of those supports Mercurial. So it's Git or get on the road. Anyhow, I'd say that the most common branching strategy is, well, not to use one at all. For single-person purposes where you aren't automatically deploying code out to a remote server, you don't usually need more than a single branch. You might still make use of multiple branches, but this is probably the pattern that I see most often with data platform professionals. Check straight into that master branch and roll on with life. But once we introduce other developers or servers or automated deployment systems and all those other complexities of real life in the business world, it turns out that branches start to make a whole lot more sense. Feature branching is a really common pattern in this space. The idea is that we create a branch off of master and commit to it locally. For example, I have a branch here called reticulate splines. I can create the branch, do whatever code changes I need to do against it, and then commit those to the feature branch. When my work is wrapped up and it's time to bring this back to the trunk, I can create a pull request and merge that code back into the master branch. Meanwhile, my colleague may have been working on a separate feature, manifest reality. Note that when my colleague created that branch, I had not yet completed my changes. So we're working on our changes concurrently, but without interrupting each other. I don't have to care if my colleague's build is broken, and my build breaks won't affect my colleague. But part of the way through, I finished up my work and created a pull request to master. My colleague will eventually want to get those changes from master into the manifest reality branch to reduce the risk of a merge conflict where both of us edit the same files and Git's commit system can't guarantee that it can automatically merge those changes together. That's feature branching at a really high level. Next up, let's talk about environmental branching. Environmental branching is a lot like feature branching, just with one added complexity. We have multiple environments. In this example, I created a branch to work on reticulating splines. My colleague may also be working on manifesting reality, though I didn't want to add that complexity to this image because I only have so much space to show it to you. Just as before, my branch comes off of master, as that's where my production codebase will live. I work in the feature branch until I'm satisfied with it. Then, when I'm done, I can perform a pull request to a development branch. That development branch originally came from master. Then, our automated systems, after I PR to dev, could deploy that code to development servers, and we can repeat the process for however many environments we have. QA, staging, pre-production, whatever you call them. Importantly, we would create new pull requests for each of these environments, and then a final pull request for going to production in the master branch. Now, you might be wondering why we do that and don't just merge dev into QA, QA into staging, staging to pre-production, and so on until you get to production. The reason for this is we don't know what kind of detritus is floating around in the dev branch. My assumption is that as I'm working to get my code out into prod, there are other people working on it at the same time, and even though I'm ready for my code to move, they may not be ready. Therefore, if we move dev into QA, we're moving all of the code changes, including the ones which have not been verified as ready. That's a no-go, and so we instead merge in the minimum necessary change. That is, the changes in my branch versus the current production, and go from there. In order to support environmental branching, we need one more step to happen occasionally, and that is cleaning up those lower environment branches. We will inevitably have some releases which don't make it into the prod branch. They just stick around in dev forever. Instead of having them hang out there until the end of time though, we can occasionally say, that's fine. We're going to make dev look just like the master branch. We're going to push all the changes from master back down to dev and ignore everything that was in dev before. We'll eliminate all of those partially completed or abandoned code changes. And you might do this maybe once every 3 months or 6 months or whatever. It's usually a good thing though to keep this on the calendar and do it periodically, and also let those developers know beforehand that it's going to happen so that they don't lose their changes. But what this will do is it'll prevent errors popping up in lower environments due to abandoned code changes where that's not the behavior in QA, but it's happening in dev because somebody forgot that there was a partial release that went out to dev and the ticket got canceled or whatever. So that's environmental branching. The last strategy we'll talk about is release branching. Release branching is a bit different from environmental branching. Here, we still have our master and dev branches, but new feature branches spawn off of dev rather than master. In other words, our lowest level dev branch is the starting point, rather than our production branch. Team members can work on their feature changes, committing until they're satisfied, and then create a pull request to dev. In order to complete the pull request, we'll usually run the code through a battery of unit and integration tests, have manual reviews, and do whatever else needs to happen in order to have an acceptable level of code quality. Once that code is in dev, we close the feature branch and we no longer need it. Periodically, we take the dev branch and create a release candidate. I called this particular release candidate R5, assuming that we had 4 prior releases. We perform any build and user acceptance tests we need, and then we merge the contents of R5 into master. Once that code is out in production, we continue working on new features against the dev branch, but sometimes bugs make their way into the wild. To fix a bug, we might build a hotfix branch off of master, perform the fix, and then merge that fix back into master. Then, when the bug is officially gone, we can merge the code change back into the R5 branch, and then eventually to dev. By doing it this way, we ensure that the untested or unapproved code in dev doesn't slip into the master branch, though it does mean that we're basing our new branches, the feature branches or hotfix branches, off of either dev or master, and so developers need to be careful that they know what branch they're originally working from. Given these 4 styles, I'll admit that for personal work, I just typically use single branch configuration and push to master directly. But in a work environment, I prefer the environmental branching technique. I think it's a little easier to work with than the release branching style, particularly for internal product teams at a company rather than a distributed group of individuals working on an open source product at different times of day and different days of the year. So what this means is these different branching strategies, and I did not cover all of the possible strategies, but there are different cases in which one strategy is better than another and others in which the roles would reverse. Now, the reason that I wanted to spend so much time on this topic is that we're going to use this environmental branching technique in the upcoming demo. So let's hop into the demo and check out our GitHub Actions workflows. What we ultimately want to do is automate the training of Azure ML pipeline runs, like in this Chicago parking tickets code first experiment. To do that, we are going to create GitHub Actions workflows, which automatically call Azure ML pipelines when we commit code to a specific branch, dev for the development workflows, and master for the production workflows. Now that we have an idea of what we are going to do, let's get it done. To kick off this demo, we are in Visual Studio Code. Inside here, if I drill into the pipeline folder, we can see a copy of the code we went through in a prior video with 2 minor changes. First, I have a requirements.txt file, which is a script we can use to tell pip or conda that we want to install certain Python packages. In here, I have 4 of them: pandas, NumPy, the Azure Machine Learning v2 SDK, and Azure Identity. The other change is in deploy score.py. If I scroll all the way down to the bottom, we can see that I no longer wait for results and no longer save prediction results in the current directory. Instead, I replace that with a note indicating where we will find predictions.csv once everything is said and done. Now let's switch to our GitHub repository and drill into the .github folder. Inside there, I have a workflows folder which contains 4 GitHub Actions workflows. I'll select train model dev.yaml so we can look at it together. On lines 3 through 6, I specify permissions and grant right to ID token. If we don't do this, we might run into problems logging into Azure later on, so make sure you've got this block at the top of your workflow. Lines 10 through 21 tell us under what circumstances we'll trigger this workflow. There are 2 such circumstances, either manual or on push. Drilling into the push side, not all code pushes will trigger this workflow. Instead, we need to push to the dev branch and we have to push at least 1 file in the paths list. We can see here that I'm only interested in changes to the AML training code or to this GitHub action workflow, not to presentation files, scoring scripts, or other workflows. Supposing that we do trigger an event, then we move into the jobs section. Inside here, I have a single job, deploy ML training pipeline. We can see the name of the job right there. This job will run on a GitHub hosted virtual machine running Ubuntu Linux. We've also specified the development environment. Remember that in the prior video, we created development and production environments and also created separate secrets for each environment. This is how we indicate that we want to use secrets from one environment versus the other. After that definition, we have the steps that we'll run. My first step is to check out this repository onto the GitHub Runner VM. Then I'll use a run command to make sure that the Azure CLI is installed, and then install the Azure ML extension to AZ CLI. Now in practice, I know that this VM will have AZ CLI pre-installed, but it probably won't have the AML extension, and this only takes a few seconds. Note that the run command executes commands at a shell, and because I have multiple lines of shell command that I want to use, I have a pipe character after the colon to indicate that this is a multi-line script. Once I've confirmed that I have the Azure CLI, the next step is to log into Azure. I'm going to use the client ID, tenant ID, and subscription ID secrets that we spent so much of the prior video putting together. And because I'm using a service principal and OpenID Connect, I'll set Enable AZPS Session on. If I were passing a client secret instead, I would not need this parameter. The next step is to ensure that I have Python on the VM, so I'll use a GitHub action called setup Python. We'll install Python 3.10, though note that this is base Python, not the Anaconda distribution. For that reason, the next step will have us jump into the pipeline folder and install dependencies from requirements.txt, ensuring that we have all of the libraries we need to perform this operation. After that, I'll create an Azure ML configuration file in the .azureml folder. I need to write out the subscription ID, resource group, and workspace name into a file called config.json, and that's what the AML SDK will use to know how to get to my workspace. Finally, we run a Python command to execute the code and deploy train.py. That's the training script. Let's take a brief look at the scoring script to see how it differs. We can see that things start off similarly with the permissions block, followed by the name and on blocks. Inside the paths list, though, we only care about cases when somebody adds a new data file or updates the scoring script or this workflow. In the jobs block, the code is almost exactly the same. We check out the repo, install the Azure CLI and ML extension, log in using our secrets, install Python, install requirements, create a config file, run a Python script. The only difference is that we're executing deploy score.py instead of deploy train.py. Let's say that we want to add our code and run a new training pipeline. Let's also say that we want to do this the right way, and that we're going to use environmental branching as our strategy here because our team decided on that as the best approach. Let's switch over to the Issues tab in GitHub and then create a new issue. I'll entitle that issue Add Code, and then I'll add a quick comment that we're going to add code to this repository, because otherwise, how useful is this repository? I could also assign this issue to somebody or add labels, but this should be good enough for a start. Note the issue number as we're going to reference it later on. Now I'll switch over to GitHub Desktop, where I've already got this repo loaded. In the current branch dropdown, I'll create a new branch and call it training-code. This creates a branch for me locally, and I'll be able to make whatever changes I need to. I have the code already in a folder called pipeline, so I can copy that folder and paste it into the repo I'm using for this video demo. This is the same code base that we looked at in Visual Studio Code, so there should be no surprises here. In GitHub Desktop, we can see all of the newly added files, so let's make sure they're selected and add a commit message. In the message description, I'll reference the issue number so that we can tie things together, and then I'll commit these changes and push them into the training code branch. At this point, if I pop over to the Actions page, we can see that nothing has changed. None of our workflows have triggered. The reason for that is we haven't committed a change to either the master or dev branches. To make such a change, I'm going to navigate to the pull requests page and create a new PR. I'll choose dev as the base and compare it from training code. In creating the pull request, I can give it a title or accept the one that it gave me. I'll also add a comment that closes this issue that I tagged before. Whenever we use a phrase like closes or resolves next to an issue number, GitHub is smart enough to tag the issue with this pull request and close it for us. Let's create the PR, and then I'll approve it. Now I can merge the pull request into the dev branch. It only takes a moment for this merge to complete, and once it's done, I can navigate to the Actions page and see that we have 2 action workflows triggered, one for dev training, one for dev scoring. Let's drill into the training workflow and see what it looks like. We have one job: deploy the training pipeline. Clicking this, we can see that the logs are updating in real time, so we can watch this for changes and react quickly if there's a problem. That said, this job will take a few minutes to complete, so I'm going to pause for station identification. Okay, now the action has finished, and we can see the end result is a successful run. I can also drill into each of the log sections and see details, including echo statements from our action at workflows, console outputs from commands we run, and print statements from Python. So if we wire up our scripts with enough diagnostic information, we can tell what's happening along the way. But it's important for us to understand what success here means. It does not mean that the Azure ML pipeline ran successfully, only that it started successfully. Now let's navigate to Azure ML Studio and take a look at that job. Here we are in Azure ML Studio. If I navigate to the Jobs menu and choose the Chicago Parking Tickets Code First experiment, I can see that there is one run called train_pipeline, which is currently running. We should also note that a service principal created this run rather than an individual user like me. Now, because we've already looked at this pipeline in prior videos, I won't have us sit around until it's completed, but I will note that we used a pull request into the dev branch to launch an Azure ML pipeline. When I perform a pull request into the master branch, I'll have the prod workflow kick off, and we would have another round of model training in an Azure ML workspace. We could certainly make this pipeline more sophisticated, such as waiting for the training pipeline to finish and update our GitHub action logs with those details, or including in our Python code some webhook call to create a GitHub issue if the code fails for some reason. But what we have right now is already pretty useful, and so we're going to call it a day. And that's going to do it for GitHub Actions. Over the prior couple of videos, we have gotten a better understanding of what MLOps is, as well as how GitHub Actions fit into the story. In the next video, I'm going to pivot to a data science-friendly tool for handling large data sets, as we don't want to store those in our Git repos. Be on the lookout for that video. We'll have links and show notes in the description below, and until we see each other in the next video, take care.